Welcome everyone to our second video on chapter 13. We're going to again continue our discussion of solutions. Okay, in this video we're going to talk a little bit more about just some examples of things that dissolve with each other, right? And just re-emphasize this point of like dissolves like, and how our intermolecular forces between solute and solvent need to be similar with the intermolecular forces between solute and solvent. Okay. So again, in this first example, right, if I were to try to place something like sodium chloride and hexane, right, where hexane is my solvent, sodium chloride is my solute, right? In this case, right, my solute has very strong forces, right? These have ionic bonding, right? Right? These are very strong intermolecular forces. Okay. Hexane has dispersion type of intermolecular forces between other hexane molecules, right? My solvent intermolecular forces are dispersion, right? These are very weak, right? And so my intermolecular forces that exist between hexane and sodium chloride, right, is just, right, between these two is just going to be the dispersion type intermolecular forces, right? Because right, hexane has no other type of intermolecular forces, right? There is no dipole-dipole interactions, no hydrogen bonding or anything like that in hexane, so it's only going to have these dispersion forces, so it's only going to exert dispersion forces on sodium chloride, right? And so if I want to dissolve sodium chloride in hexane, right, that sodium chloride has to break apart, which is because of these strong forces holding it together, requires a lot of energy to break apart. But now I have these weak interactions between my solute and solvent, and so those weak interactions are not going to gain me much energy back when I mix these things together, and so it's not going to want to do this, right? And so that's why sodium chloride does not dissolve in hexane, because there's not a strong enough interaction between the solvent and the solute to break apart the solute particles from each other. Okay. Another example here, right, is if I were to consider dissolving ethanol in water, right? Ethanol, like water, has hydrogen bonding interactions between those two ethanol molecules, right? And ethanol with water also has this hydrogen bonding type intermolecular forces, right? So when I try to dissolve ethanol in water, right, I'm breaking apart some hydrogen bonds between different ethanol molecules, but then I reform new hydrogen bonds between the ethanol and water, and so these things are going to easily mix with each other. Okay, because they have very similar intermolecular forces between solute, solvent, and solute. Okay, there's three different types of molecule, types of pairing, right? I can pair two solutes together, I can pair two solvents together, or I can pair the solutes and solvent together. All three of those pairs have similar intermolecular forces, and so those things will mix very easily. Right? Another example here is, let's say I'm looking at cyclohexane, right, versus glucose, okay? And I want to try to dissolve these things in water, right? Well, cyclohexane, right, is just a pure carbohydrate. This just has dispersion interactions, okay? While glucose here has a bunch of these OH groups, which means it's going to have hydrogen bonding type intermolecular forces, right? Well, our solvent here is water, right? H2O, which also has hydrogen bonding, right? And so that means, okay, that things like glucose can easily dissolve in water because it has similar intermolecular forces with that water, but cyclohexane will not dissolve in water. And this time it's easy to break apart the cyclohexane molecules because they just have dispersion interactions, right? So they're not very strong forces holding them together. But I also have to break apart my solvent molecules, right? I have to break the water molecules apart to fit in the cyclohexanes. And the water's got these very strong hydrogen bonding interactions. And so it's not going to want to break apart to then fit in these weak dispersion intermolecular forces that are involved with cyclohexane. And so water's not going to want to fit that cyclohexane in because of these weak intermolecular forces that exist in cyclohexane. And so cyclohexane will not dissolve in water, while glucose will easily dissolve in water. Okay. Another example of this, right, is talking about things like vitamin A here, right? In this case, right, you have most of the molecule is very non-polar, right? So there's very large, just carbohydrate groups. But at the very end, you do have this hydrogen bonding interaction, right, with this OH group. So you try to dissolve this in water, and it will dissolve in water, okay? Not a lot, but it will dissolve somewhat in water because it does have this hydrogen bonding. But the problem is, right, to dissolve vitamin A, right, I'm getting some favorable hydrogen bonding interactions with waters near, right, this end of the group. But to fit all of vitamin A in here, right, I still got to throw a bunch of water molecules all around this guy, right, in order to fit in this guy in solution, okay? And so, right, so I'm going to break apart a lot of hydrogen bonds to only get a couple back, right? And so vitamin A, while soluble in water, is not very soluble, okay? And it's because, again, most of the molecule is very nonpolar, just that dispersion interactions only part of the molecule does, right? While our other example here, right, I have a lot of potential hydrogen bonding interactions all over the molecule, okay? All these different oxygen and hydrogen groups attached to the oxygens, right? So there's a lot of different places where you can have hydrogen bonding occur. And so when I break apart these water molecules, they will be able to form a lot of hydrogen bonding with this solute, okay? And it will dissolve very easily and readily in solution. Okay, so to further emphasize this point, right, we look at the solubility of certain alcohols, okay, in water, right, where as I'm going from the top of this table to the bottom, right, I'm increasing this bulky chain, right, this bulky carbohydrate chain that just has dispersion interactions, right. Along here, I just have dispersion interactions, right, and then at the very end, I have this H bonding, right? And so we look at the solubility in something like water, which is a very polar solvent, and something like hexane, which is a very non-polar solvent, right? We see things like methanol, ethanol, and propofol are very soluble in water. They'll completely mix. This infinity is just indicating that they're completely soluble, right? I can mix as much as I want together of these two compounds, and they will always mix together, okay? But when I get to things like hexanol, right, it is soluble, but not a lot, right? I can mix a little bit of hexane or hexanol in water and it will dissolve, but not a lot. And again, it's because I got to break apart a lot of water molecules to fit in this hexanol, and there's a lot of that hexanol that just has dispersion intermolecular forces, and so it's not going to optimally dissolve, right, in this solution, right? While if I look at the reverse case of these nonpolar solvents, okay, right, like the hexane, okay, when I try to dissolve methanol, right, well, methanol has a lot of strong hydrogen bonding interactions with other methanol molecules, okay, and so the methanol has to break apart a lot of these hydrogen bonds to then form dispersion intermolecular interactions with the solvent hexane, okay, and that's not very favorable, right? And so the methanol is not going to be very soluble in that hexane. It does dissolve some, right? But it doesn't mix a lot, right? While all the other alcohols, because they have bigger and bigger dispersion groups, right? Each one of these alcohols, as I go further down this table, has more and more carbohydrates, and it's going to have more and more, most of the molecule is going to become just dispersion in molecular forces. And so now I have very similar intermolecular forces between my solute and my solvent, and so they mix very easily, right? And so these are just some of the examples, right, of the different types of solute and solvent combinations we can be talking about and how soluble things can be, right? It's not just that something is soluble or isn't soluble, right? If something is soluble, there's different levels of solubility, and later on in this chapter, we'll talk more about how we describe how soluble something is. Okay. And just to wrap this up, right, just talk about, right, in this table, right, it talks about admissible and immiscible, right, and this just describes mixing of two two liquids together, right? If I mix two liquids together and they mix completely, then that is miscible. If I mix two liquids together and they don't mix completely, that is immiscible, right? Things like oil and water are obviously immiscible liquids, right? While something like methanol and water would be miscible liquids.